So here we're going to look at a special case. What happens if we apply all of this technology we've just been developing, T and B frames and whatnot, to a graph of a function? So to hook up with the way we've been doing things, we first need a parameterization. Remember, we'll use the Monge parameterization. Since we have a free variable, independent variable x, we'll use that as our parameter. So x equals x, and then y is f of x, and we'll just set z equal to 0 because it's a curve in a plane, but we'll pad this out so it's compatible with our other stuff. Our parameter, by the way, has domain a to b, just like our graph of our function. Okay. Maybe one thing to mention is, first of all, let's consider arc length. Okay. All right, well, remember for arc length, we need the derivative of our parameterization. So that would be 1 f prime and 0. And we need the length of our derivative. This would be the square root of 1 squared plus the derivative of f squared plus 0 squared. So it's just the square root of 1 plus f prime squared. And so what is the arc length for this guy? It'd be the integral from a to b. That's the domain for our parameter. And then we have the length of r prime, which is 1 plus f prime of x quantity squared dx. And what do you know? There's our arc length formula, may be familiar from calculus 2, right? That's our old mysterious arc length formula. It makes sense here. Way to see why it looks this way is, this is dx squared, and then it's adding to that dy dx squared, right? It's just that dx is 1. So, okay, so there's arc length. Now let's look at, how about curvature? So we have r prime already is 1 f prime and 0. We need r double prime, so that would be 0 f double prime 0. Let's take the cross product, and let's see, the I component 0, j component 0, and the k component will just be f double prime. And so we know that curvature is the length of the cross product of the first two derivatives over the length of the first derivative cubed. And so this comes out to be, let's see, the length of the cross product here would just be, and be careful, it's the absolute value of f double prime divided by, we have 1 plus the derivative squared, that square rooted is the length of r prime, but we have it to the third power, so it's to the 3/2 power. And so there's a formula for curvature. Keep in mind this only for the graph of a function, y equals f of x. But in the case that you have a graph of a function, that's a very easy formula to use. Maybe to complete this picture, how about torsion? Of course, we know that what the answer is for torsion if you pause and think about it for a little bit, because what kind of curve do we have? But let me go ahead and actually compute this. We have r prime cross r double prime dotted with r triple prime. Notice that the if we dot these two guys together, we get 0. And so the torsion for a graph of function is 0. But of course that's true. We have a planar curve, right? So it makes us feel silly, maybe. Okay, now let's make it concrete. Okay, let's do an example just to show how easy it is to use this. So in particular, discussing curvature, what if you have a parabola, right? Well, so curvature is absolute value of the second derivative over 1 plus the first derivative squared raised to the 3/2 power. And let's see, we know that y prime is 2x, y double prime is 2. So we have 2 over 1 plus the derivative squared would be 4x squared, all raised to the 3/2 power. what if we wanted to maximize kappa? Okay, what's the maximum curvature we experience? Well, notice to make it maximize, we would want to make the denominator small, right? And to make it small, we would need to make x equal to 0. That's the smallest it can be. So maximum curvature occurs when x is 0, and the maximum curvature comes out to be 2, because it's 2 over 1 raised to the 3/2 power. What happens to the curvature as x moves away from the origin, as the absolute value of x increases? Well, then you would have that this denominator here is getting really, really big. The numerator stays fixed, so it's heading to, it's basically becoming 1 over infinity. It's 0, right? What is this? Let's see, what does our graph look like, right? So we have a parabola. Let me try again, so it looks more like a parabola. Okay. We have our parabola here, right? And where is it bent the most? Well, of course it's bent most at its vertex. And what we just found out is if we wanted to draw an osculating circle there, the radius of that osculating circle would be 1/2, right? And as we get further and further out on the parabola, it looks more and more like a straight line, and so curvature is going to 0. Right? There you go.